Okay, today we want to go over the very basic definition of Heaviside function. And because the video I uploaded last time, it was a little bit advanced, so I decided to make a shorter and more basic video for Heaviside function. So let's go ahead and create a note here, if I can access my notes. Alright, I'm gonna add one page here, so let me say draw. Okay, so can I get rid of this pen here? Maybe I should rotate the screen. Can I rotate the screen? See, yep. Rotate the screen, and now we want to define a function called Heaviside x minus a, which we show it with this notation, like a bracket, x minus a. And the definition of this function is if your x is greater than a, then this function returns x minus a inside parentheses, or itself, x minus a. If your x is smaller than a, then this function returns 0 or null, nothing. So for example, Heaviside x minus 2, if I want to plot this function, this is my x-axis and this is my y. Let's say this is my y function. I want to plot y versus x. So here at location 1, 2, -1, -2, according to the definition on top, if my x is smaller than 2, I should get 0. So for everything before 2, this function is going to return 0 to -infinity. And for everything just after 2, this function is going to return, let's use a color, another color. This function is going to return x minus 2, which is a line. Okay, so x minus 2 is equal to 0 at here, and then you have a slope like this. So that's the plot of Heaviside x minus 2. And as you can see, this function is piecewise continuous. That means that the function is always continuous, but on different intervals. And that means, according to the definition of piecewise continuity, the derivative doesn't have to exist at this point too, but it must be continuous. Okay, so this is basic definition of Heaviside function. Now how can I use it in practice? In order to use that in our field of civil engineering for shear moment diagram and consequently finding the beam deflection, things like that, you can always make things simpler by using Heaviside function. For example, let's say if I have a beam that is fixed to the wall, and then right here at the middle I have, for example, a vertical force of 2 kilonewton. Okay, so the beam is loaded, it's fixed at one side to the wall and the other side is free, and there is a 2K force in the middle, and let's say this distance is 1 meter, again 1 meter. Okay, now if I want to draw a shear moment diagram for this, I have to, as we discussed many times, I have to take two separate intervals from here to here, and then from here to here. So I have to do everything like twice. Drawing FED, writing equation, finding the internal moment and everything. Now imagine if instead of 2K, if I have more forces, then I have to do this many, many times. Now the question is, how can I use Heaviside function? Well, in order to use Heaviside function, you just cut this thing, either take it from the left or from the right, your reference point. I take my reference point from the left, and then cut to the very end that includes all the loading. You see, this cut is not, if this point is A, B, C, this cut is just before point C. That it includes 2K force, the wall reaction, and everything. So this is my X. Now draw FED. If I draw FED, this is the second step. If I draw FED for that, then I get this. This is my cut. This is wall. At wall, I have a vertical force 2K upward. The wall reaction. Well, you can easily find a wall reaction using equation in vector statics, right? It's not a big deal. So you have 2K up, and then you also have a couple moment at the wall, which is 2 kilonewton meter, to cancel the effect of this 2K in the middle, right? The opposite direction. Then you have another 2K here, and then you have internal couple moment or internal moment right here at point X, and then you also have internal shear at X. So that's your full FED for this problem. And from here to here, don't forget that from here to here is X. Now we want to use Heaviside function, which I'm just highlighting. I'm talking about this definition, in order to create one single equation for moment relation across this beam instead of two different relations. Okay, so what should I do? Well, I say write summation of moment about point X is equal to 0. Back to vector statics. So I start with the point X and I write moment equation. Well, the first thing is m at X, positive or negative? Positive. Vx is passing through X, so it doesn't have any couple moment, right? So the moment contributed due to Vx is 0. Then you go to 2K, this one. Let's put a circle around it or highlight it. This 2K I'm talking about, this 2K, okay? Now, in order to find the moment of this 2K with respect to point X, you have to find this distance from here to here. What is that distance? That distance is Heaviside X minus 1. Why? Why I didn't use parentheses X minus 1? Because if my cut, look at the cut, the X. You see this cut? If my cut, if I scroll it to the left, just before the 2K force, there is no 2K, right? There is nothing. So I expect that my moment contributed from the 2K should vanish when my X is smaller than 1. That's exactly what the definition of Heaviside function is doing it for me. It's like a switch. Okay? If I put parentheses, the one on the bottom, it doesn't go to 0. You can easily see that it becomes 2K times parentheses X minus 1, and when your X is less than 1, you get a negative moment contributed from 2K, which is not physical, right? So in order to add the contribution of 2K force right here, I say mx plus 2K times the moment arm, which is Heaviside X minus 1. That's it. Now I go to the one and the wall, the 2K right here. This 2K is always there regardless of where I put my cut. If I put my cut after 2K or the cut here before 2K, it doesn't matter. This 2K at the wall is always there. So I just consider it as a regular force. It's not, I don't need any switch to put it on or off because it's always there. So I simply say I treat it like old way I used to do it before I introduced a Heaviside function. So I simply say that becomes 2K times moment arm, which is x, positive or negative? Negative. So negative 2k times x. The last thing I have to include is the couple moment at the wall. Talking about 2 kilonewton meters right here. Again, that couple moment exists regardless of where I cut the beam. Okay? So I just treat it like old way. So I say simply plus 2k. There is no x required. It's couple moment. You don't need a moment arm. Is equal to 0. That equation, if I solve it for mx, is going to give me my moment diagram. Don't forget, this is just one line. If I wanted to use the old method, I had to have 2 different cuts and then 2 different relation, and like twice the work, right? So if I solve for mx, I get mx is equal to negative 2k times Heaviside x minus 1. So I took this 2k here is positive, I took it to the right, negative 2k times Heaviside x minus 1 plus 2k times x, negative 2k. That's it. That's my moment diagram. Highlighted. Just one beautiful equation, one line. Now I want to find deflection at point C. Again, if I want to do that using traditional method, I have to take 2 intervals and each one give me 2 extra constant of integration, right? You have done this before, so I want to do it right now with Heaviside function. What do? I write the equation. Second derivative of deflection is equal to mx over ei. Take ei to the one side and consider as a constant. So you get ei times second derivative deflection is equal to m of x, which is simply this equation, right? So I just plug it here, the m of x, and then I go ahead and do double integration, right? So if I do that, I get ei, the second derivative of v. I really don't like iPad. Not now. Okay, the second derivative of v with respect to x is equal to negative 2 Heaviside x minus 1. And there is a k here, negative 2k x minus 1 plus 2k times x, negative 2k. Okay, go ahead and take the integral of this, so you get ei dv dx is equal to negative 1k x minus 1 to the second power plus 1k again x2 negative 2k times x plus c1. So all I did, I took the integral of both sides of this relation. On the left you get ei dv dx, on the right you get negative 1k. This I need to write it more clearly. So this is negative 1k. Heaviside x minus 1 to the second power. Don't forget, now when we want to take derivative or integral, we treat Heaviside function like parentheses. You see, like x minus 1, how do you take the integral of that? Right, you get x minus 1, 2 over 2. Right? If you treat Heaviside like parentheses, when you take integral, you just get x minus 1 square over 2. And the 2 cancel out with these 2 right here on the left, so you get negative 1k Heaviside x minus 1 to the second power. Now go ahead and take integral of second term, this term right here, so you get again 2k times x2 over 2, 2k cancel with 2, you get 1k x2, and finally negative 2k times x plus c1. So again, you see you have a constant of integration right here. How can I specify that? Well, you specify the boundary condition. you say I have this condition dv dx, which is a slope at x0 is equal to 0, right? So if you substitute right here, your left side at x0 is 0. Your right side is negative 1k. Instead of x, put 0 minus 1 second power plus 1k. X is equal to 0 second power, negative 2k times x is equal to 0 plus c1. So again, this one, because x0 is smaller than 1, this is identical to 0, right? So immediately this is 0. This is by definition of parentheses 0. This is also 0. So your c1 is equal to 0. Now, let's go ahead and do another integral. If I do the second integral, then I get, look, I'm taking another integral of this relation, with c1 is equal to 0. The second integral is ei v of x is equal to negative 1k x minus 1 to 3 over 3. Raise this bar. Okay. So ei v of x is equal to negative 1k x minus 1 to 3 over 3 plus 1k x to the 3 over 3 negative 2k x over 2 x2 over 2 plus c2. Okay, now what do I get for c2? Well, you have this second boundary condition, say v, the deflection at x0 is equal to 0 because it's wall, right? It's a wall condition. So if you put 0 right here, this is simply the integral of that. You see ei v of x is equal to negative 1k x minus 1 to the 3 over 3 plus 1k x3 over 3 minus 2k x2 over 2 plus c1 times x, but c1 was 0. That's the reason I didn't bring it. Plus c2. This is the second constant of integration. Now we want to find this using the second boundary condition. If I put v of x is 0 right here, you get 0 is equal to, the first term becomes 0 plus 0 plus 0 plus c2. So that means c2 is also 0. Okay? So if I put it all together, I get ei v at any x is equal to negative 1k over 3 x minus 1 to the 3 plus 1k over 3 x being minus 1k x2, and c2 is also 0. So that's my equation of deflection for neutral axis. It's a cubic equation. Now the objective was to find the deflection, or v at x is equal to 2 at the end of the beam. Look at here. The x location of point C, or the end of the beam, is 2, right? So substitute x is equal to 2 there. So you get the deflection at point C, which is v at x2, is equal to negative 1k over 3. Instead of x, put 2. 2 minus 1, 1. Heaviside 1 is just 1 to the cube, so it's 1 plus 1k over 3 times 2 third power minus 1k times 2 to the second power. That's it. So if you do this algebra right here, then you get negative 1k over 3 plus 8k over 3 negative 1k times 4, and if you multiply by 3 you get another 3 here, and then you just add all the numerators, so 3 goes to the bottom, negative 1k plus 8, 7k minus 12k, which is equal to 3, and for 5k, negative 5k over 3. Okay, so this is the deflection at point C, and don't forget there is also EI multiplied by that on the left. So the deflection at point C is equal to negative 5k over 3 EI. Negative 5k over 3 EI. Now imagine if you wanted to solve this problem using the traditional method we use in this class, taking two different intervals and applying continuity equation at the point B right here in the middle to get rid of those extra constant integration. It's going to be a big mess, and I recommend do it. It takes some time, but the end result should be the same right here. You should match the same result, only your derivation gets a little bit longer. Now in the next video I'm going to solve a more complicated problem that you have like three different kind of loading, or you have a different boundary condition. Like instead of having a wall right here, you may have a pin here and a roller right here, right? How can we use those problems? How can we solve those problems using Heaviside function? That's the topic of the next video.